You know that feeling when you finish a show and Netflix instantly recommends something new and it's perfect? Almost spooky, right? How does it know?
Or how about this? How does Amazon figure out the single best route to get a package from a giant, chaotic warehouse all the way to your specific front door, millions and millions of times a day?
And let's get even more basic. The phone in your hand, how does it actually think? How does it make decisions based on nothing but pure logic? Well, it might all feel like magic, but it's really not. All of these incredibly complex systems are all built on the very same elegant, powerful, and, well, mostly invisible foundation. They're all speaking the same secret language. So, let's pull back the curtain. Today, we're decoding that secret language. We're going to dive into discrete structures and optimization, which is just a fancy way of saying we're exploring the hidden rules that bring order to our entire digital world. We're going to tackle this in 5 key parts. We'll start with the absolute basics, the rules of thinking clearly. Then we'll get into the art of counting really, really big things. After that, we'll see how the world is just a network of connections, find the hidden patterns within those networks, and finally, learn how to make the absolute best, most optimal choice.
All right, first up, the rules of reason. Think of this as the bedrock for everything else. Before we can build anything, we have to establish a perfectly clear way of thinking.
The main tool here is something called propositional logic. The easiest way to think of it is as a grammar for logical arguments. It's a system for making statements that can only be true or false. There are no maybes, no gray areas. It's that absolute precision that computers need to function.
And this logic is built from just a few really simple but powerful ideas. We use sets just to group related things together. We use relations to show how those things are connected. And then we use Boolean algebra. That's the math of true and false, or ones and zeros, to make decisions. That's it.
So why does this matter? Because this isn't just theory. This is literally the blueprint for the microchips in your laptop and phone. It's how databases can search through billions of files in a split second. This is the absolute foundation of all digital logic.
Okay, with our foundation of logic set, let's build on it with our next section, the art of counting. Now, I know what you're thinking. Counting sounds easy, but trust me, it gets complicated, and it gets complicated fast.
So here's a key question. Does the order matter? Let's say you're awarding medals at the Olympics. Gold, silver, and bronze. The order you pick the athletes in matters a ton, right? That's a permutation. But what if you're just picking 3 people to form a team? The order you pick them in doesn't matter at all. The team is the same. That's a combination. Knowing that difference is absolutely crucial.
And in counting, you also get these beautifully simple rules, like the pigeonhole principle. It sounds obvious, right? If you've got more pigeons than holes, one hole has to have more than one pigeon. Duh. But you would be absolutely amazed at the powerful and deep things you can prove using just that one simple idea.
And the reason we care so much about counting is simple. Once you can count all the possible outcomes, you can start calculating probabilities. This is the engine behind data analysis, understanding financial risk, and even concepts like Bayes' theorem, which helps AI systems learn by updating their beliefs when they get new data.
All right, let's zoom out. We've been looking at individual items, but now let's talk about the relationships between them. It's time for mapping the connections.
So, what do all these things have in common? Your friends on Instagram? All the flight paths that crisscross the globe? The very structure of the internet itself?
They're all networks, and the mathematical tool we use to understand them is called graph theory. And honestly, the core idea is super simple. A graph is just a collection of dots, which we call nodes, and the lines that connect them, which we call edges. That's really all there is to it.
But don't let that simplicity fool you. That simple idea of dots and lines is incredibly powerful. It's what lets your GPS find the shortest path. It helps us model how a video goes viral. We use special structures called spanning trees to design efficient computer networks, and it's the key to solving famously difficult logistical problems like the traveling salesman problem.
Okay, now we're going to get a little more abstract, but this might just be the most profound tool of all. We're going to talk about uncovering hidden patterns, finding that deep underlying order in things.
This is where something called group theory comes in. You can just think of it as the mathematics of symmetry. A Rubik's Cube is the perfect example. There's a limited set of moves you can make, right? And those moves have a hidden structure. Group theory is the language we use to describe that structure. Whether it's in a puzzle, in modern cryptography, or even in the fundamental laws of physics, it's a way to understand the secret rules that govern a system.
And that brings us to our final section, which is where we put everything together. This is about making the perfect choice. It's the science of optimization.
So let's look at a classic business problem. Imagine your factory makes two products, widget A and widget B. They each have a different profit margin, and they use different amounts of your time and materials. Now, you only have a limited amount of time and materials. So the million-dollar question is, what's the perfect mix of A and B to make the most possible profit? This is what we call a linear programming problem.
Now, the algorithms to solve this can get really complicated, but the idea behind them is beautifully intuitive. You just start with any possible solution that fits your limits. Then you look for a tiny change, a little trade-off that can improve your result. And you just keep making those small improvements over and over until you get to a point where you simply can't improve it anymore. And right there, that's your optimal answer.
And I'm not kidding, this is a massive deal. This kind of optimization runs our world. It's used in global supply chains to manage shipping. It's used in project management to find the critical path that determines how long a project will take. Airlines use it to schedule their entire fleet of planes and crews. It's absolutely everywhere.
So, from pure logic to complex networks to finding the perfect choice. That's the toolkit. These aren't just abstract ideas in a textbook. They are the fundamental, invisible structures our entire modern world is built on. So the only question left is, now that you can see them, what problem are you going to solve?